You think black holes are just cosmic vacuum cleaners? Giant invisible monsters in space that suck everything in and nothing ever comes out. Ever. That's what everyone says. Nothing escapes a black hole. Not matter, not light, not information, nothing. Cross that boundary, the event horizon, and you're gone forever. The universe will never see you again. Fine. That's the story. That's what the textbooks say. That's what the documentaries tell you. Black holes are the universe's ultimate trash compactors, eternal prisons from which there is no escape. But here's the problem. Stephen Hawking didn't believe it, not completely. And when he actually sat down and worked through the mathematics, when he combined quantum mechanics with general relativity in a way no one had done before, he discovered something so shocking, so completely unexpected, that it made physicists question everything they thought they knew about black holes. Black holes aren't black. They glow, they radiate, they evaporate, and eventually, after an incomprehensibly long time, they disappear completely. Everything that fell in, all that mass, all that energy, all that information, radiates back out into space. Let me show you how Hawking figured this out, and why it broke physics in the most beautiful way possible. Let's start simple. Let's start with something everyone knows, but nobody really understands. Why does anything fall at all? You drop something, it falls. We've all seen this. We've all done this. 1,000,000 times. Gravity pulls things down. Fine. But what is gravity really doing? Most people has never actually thought about this. They just say gravity and think they've explained something. But that's not an explanation. That's just a word. When you really ask what gravity is, what it's actually doing to make things fall, you discover something profound. Newton told us gravity is a force between masses. Every mass attracts every other mass. The Earth pulls on you. You pull on the Earth. The force depends on the masses and the distance between them. Specifically, it's proportional to the product of the masses and inversely proportional to the square of the distance. Double the distance, the force becomes 4 times weaker. Triple the distance, 9 times weaker. This is the inverse square law we talked about before with the moon. Newton figured this out, tested it, and it worked. It explained the orbits of planets, the tides, the shape of the Earth, everything. For 200 years, this was gravity. Case closed. But then Einstein came along, and Einstein was thinking about something weird. He was thinking about acceleration. If you're in an elevator and the cable breaks, you're in freefall. Everything in the elevator is in freefall with you. You float. You don't feel gravity. Objects around you don't fall relative to you. They all fall together. Now, if you're in that same elevator far out in space, away from any gravity, and someone starts pulling the elevator up, accelerating it, what happens? You feel pressed against the floor, exactly as if you're standing on Earth. Acceleration feels just like gravity. Einstein said, wait a minute, what if they're the same thing? What if gravity isn't a force at all? What if it's acceleration? What if being in a gravitational field is exactly the same as being in an accelerated reference frame? This led him to something extraordinary. If gravity is acceleration, and acceleration means following a path through space-time, then massive objects must be bending space-time itself. The Earth isn't pulling you down. The Earth is curving space-time around it, and you're following the straightest possible path through that curved space-time. That path happens to be toward the Earth's center. This is general relativity, and it's been tested over and over and over. The bending of light by the sun during an eclipse, exactly as predicted. The precession of Mercury's orbit, explained perfectly. Gravitational waves, detected a century after Einstein predicted them. It works. General relativity is right. Space-time really does curve. Now here's where it gets interesting for black holes. Imagine you're standing on the surface of the Earth and you throw a ball straight up. The ball goes up, slows down, stops, and falls back down. You throw it harder, it goes higher. Throw it at 10 meters per second, it goes up maybe 5 meters. Throw it at 100 meters per second, assuming you could, and no air resistance, it goes up about 500 meters. There's a pattern here. The harder you throw it, the higher it goes. But here's the key question. Is there a speed where if you throw it that fast, it never comes back? Yes, absolutely. There's a speed where the ball has just enough energy to escape Earth's gravity completely. We call this escape velocity. For Earth, escape velocity is about 11.2 kilometers per second. That's roughly 25,000 miles per hour, about 40,000 kilometers per hour. Throw anything that fast straight up, and it'll leave Earth forever. It'll slow down as it climbs out of Earth's gravitational field, but it'll never slow down enough to stop and fall back. It escapes. Let me make sure this is clear because it's important. Escape velocity isn't the speed you need to maintain. It's the initial speed you need. Once you're going that fast at the surface, you can turn off your engines. You don't need any more thrust. You'll coast away forever. Your speed will decrease as you climb, but you'll never stop. That's escape velocity. And here's the beautiful thing. It doesn't depend on the mass of the thing you're throwing. A feather and a cannonball have the same escape velocity. It only depends on the mass of the object you're escaping from and how far you are from its center. The formula is straightforward. Escape velocity equals the square root of 2gm divided by r. G is the gravitational constant, about 6t7 times 10 to the minus 11 in SI units. M is the mass of the object. R is the distance from its center. Let's plug in numbers for Earth. M is about 6 times 10 to the 24 kilograms. R is about 4 million meters. Do the math, you get about 11,200 meters per second. 11.2 kilometers per second. That's escape velocity from Earth's surface. Now, what about other objects? The Moon has less mass than Earth and is smaller. Escape velocity from the Moon is only about 2.4 kilometers per second. Much easier to escape. The Sun is much more massive. Escape velocity from the Sun's surface is about 618 kilometers per second. Much harder to escape. Jupiter, even more massive but also much larger, has an escape velocity of about 60 kilometers per second from its cloud tops. Notice something. Escape velocity depends on two things: how massive the object is and how far you are from its center. If you could somehow make an object more massive without making it bigger, escape velocity would increase. If you could somehow compress an object, make it smaller without changing its mass, escape velocity from its surface would also increase, because you're standing closer to the center, where gravity is stronger. Here's where it gets wild. What if you had an object so massive or so compressed that the escape velocity from its surface was faster than light? Think about that for a second. Light travels at 299,790 kilometers per second. That's the cosmic speed limit. Nothing can go faster. We've established this. It's built into the structure of space-time itself. So if escape velocity exceeds the speed of light, nothing can escape. Not even light. That's a black hole. Let me say that again because it's important. A black hole isn't a hole in space. It's not empty. It's not a vacuum cleaner sucking things in. It's an object. It's an incredibly dense object. It's an object so dense that the escape velocity from its surface exceeds the speed of light. And because nothing can exceed the speed of light, nothing can escape. Not matter, not energy, not light itself, nothing. Now let's calculate something specific. At what radius does escape velocity equal the speed of light? Set v equal to c in our escape velocity formula. C equals the square root of 2gm divided by r. Square both sides. C squared equals 2gm divided by r. Solve for r. R equals 2gm divided by c squared. This radius is called the Schwarzschild radius, named after Karl Schwarzschild, who calculated it in 1916, just months after Einstein published general relativity. The Schwarzschild radius is the radius where escape velocity equals the speed of light. If you compress any mass inside its Schwarzschild radius, you get a black hole. Let's calculate it for familiar objects. For the Sun, with a mass of about 2 times 10 to the 30 kilograms, the Schwarzschild radius is about 3 kilometers. Just 3 kilometers. The sun's actual radius is about 700,000 kilometers. So if you could somehow compress the entire sun into a sphere just 6 kilometers across, it would become a black hole. For Earth, mass about 6 times 10 to the 24 kilograms, the Schwarzschild radius is about 9 millimeters. 9 millimeters. Compress the entire Earth into a marble smaller than a centimeter, and it becomes a black hole. For you, assuming a mass of about 70 kilograms, your Schwarzschild radius is about 10 to the minus 25 meters. That's a billion times smaller than a proton. You'd have to compress yourself to a point far, far smaller than any particle we know of to become a black hole. But here's the thing. Black holes actually exist. They're real. We've detected them, we've measured them, we've even photographed one. The Event Horizon Telescope captured an image of the supermassive black hole at the center of galaxy M87 in 2019. You've probably seen it. That orange ring around a dark center. That dark center is the event horizon, the boundary where escape velocity exceeds the speed of light. And these black holes didn't start as the sun or Earth compressed to ridiculous densities. They form naturally. When very massive stars, much more massive than the sun, run out of fuel and collapse, they compress themselves. The core collapses inward with nothing to stop it. Electron pressure can't stop it. Neutron pressure can't stop it. Nothing can stop it. The star collapses past its Schwarzschild radius and becomes a black hole. This happens. It's not theoretical. We've observed the aftermath. We've detected gravitational waves from black holes colliding and merging. Black holes are real. Now, here's where things get really strange. Let's think about what happens when something falls into a black hole. Imagine you're watching your friend fall toward the event horizon. What do you see? As your friend gets closer and closer to the event horizon, something weird happens. They appear to slow down. The light from them gets redshifted, meaning it loses energy, becomes redder. They get dimmer and dimmer, and right as they approach the event horizon, they appear to freeze. From your perspective outside the black hole, your friend never actually crosses the event horizon. They just get closer and closer, dimmer, and fade away. Time dilation near the event horizon becomes so extreme that it appears to take infinite time for anything to cross it. But from your friend's perspective, it's completely different. They don't notice anything special at the event horizon. They fall right through. No barrier, no wall, nothing. They cross the event horizon and keep falling toward the center, toward what we call the singularity. And here's the problem. Once they cross, they can never send you a signal. They can never communicate with you. Light they emit from inside the event horizon can't escape. It falls back toward the singularity, so from outside you can never know what happened to them. The information about what they were, their mass, their composition, everything except their mass, charge, and angular momentum is lost forever. This is the classical picture of black holes. Schwarzschild figured out the geometry in 1916. Reuter figured out rotating black holes in 1963. John Wheeler coined the term black hole in 1967, and the physics community developed a detailed understanding of how black holes work according to general relativity. They have mass. They have angular momentum if they're rotating. They have charge if they're electrically charged. And that's it. That's all you can know about a black hole from the outside. Wheeler called this black holes have no hair, meaning they have no other distinguishing features. Two black holes with the same mass, charge, and angular momentum are identical, even if one formed from a star and the other formed from a million spaceships. All the details, all the information about what fell in is lost, and black holes can only get bigger. Anything that falls in adds mass. The event horizon grows. Black holes can merge. Two black holes collide. They become one bigger black hole. But black holes can never get smaller. They never shrink. They never evaporate. They're eternal. Once formed, a black hole exists forever, slowly accreting more matter, slowly growing, but never disappearing. That was the picture in the early 1970s. That was what everyone believed. Except Stephen Hawking wasn't satisfied. He was bothered by something. He was thinking about the second law of thermodynamics. The second law says that entropy, which is roughly a measure of disorder, always increases, never decreases. If you have a system and you do something to it, the total entropy of the system plus its surroundings always goes up, or at best stays the same, never goes down. This is one of the most fundamental laws in physics. It explains why time has a direction, why you can scramble an egg but not unscramble it, why heat flows from hot to cold, not cold to hot, why perfume spreads through a room but never unspreads back into the bottle. Entropy increases. Now entropy is related to information. When entropy increases, information is lost. When you scramble an egg, you lose information about which atoms were in the yolk and which were in the white. When heat spreads, you lose information about which molecules had more energy. The second law is really saying that information gets scrambled, gets spread out, gets lost in the details. Here's the problem with black holes. Imagine you have a box full of gas, hot gas, high entropy. The molecules are moving randomly, bouncing around. Now you let the box fall into a black hole. The box, the gas, everything crosses the event horizon and disappears. From outside, all you see is that the black hole's mass increased slightly. But you lost all the information about the gas. You lost the entropy. The entropy of the universe appears to have decreased. That violates the second law. That's a problem. Jacob Bekenstein, a graduate student at Princeton in the early 1970s, had an idea. What if black holes have entropy? What if the black hole itself has entropy proportional to the area of its event horizon? If that's true, then when the gas falls in, the black hole's entropy increases by more than the entropy of the gas, so the total entropy still increases. The second law is saved. Wittgenstein proposed this in 1972. It was a radical idea. If a black hole has entropy, then it must have a temperature. Temperature and entropy are related thermodynamically. And if it has a temperature, it must radiate. Everything with a temperature radiates. That's black body radiation. Hot things glow. But black holes don't radiate. They're black. Nothing comes out. So how can they have a temperature? Hawking heard about this idea, and initially thought it was wrong. Black holes can't have temperature because they don't radiate. Temperature means radiation. Radiation means something escapes. Nothing escapes a black hole. That's the definition. But Bekenstein's argument about entropy was compelling, so Hawking decided to prove Bekenstein wrong. He set out to show mathematically that black holes cannot radiate, therefore cannot have temperature. Therefore Bekenstein's idea doesn't work. To do this, Hawking needed to combine two theories that don't normally play well together: general relativity and quantum mechanics. General relativity describes gravity, space-time, black holes. Quantum mechanics describes particles, fields, the behavior of things at very small scales. Usually, you don't need both. Gravity is important for large-scale things like planets and stars. Quantum mechanics is important for small-scale things, like atoms and particles. They operate in different regimes, but near a black hole, you need both. The gravitational field is enormous. Space-time is curved dramatically, but you're also interested in what happens to particles and fields in that curved space-time. So you need quantum field theory in curved space-time. This is mathematically very complicated. Hawking started calculating. He was looking at how quantum fields behave near the event horizon of a black hole. In quantum mechanics, the vacuum isn't really empty. The vacuum is filled with quantum fluctuations. Virtual particles are constantly popping into existence in pairs, a particle and an antiparticle, and then annihilating each other almost immediately. This happens everywhere, all the time. It's a consequence of the Heisenberg uncertainty principle. Energy can be borrowed from nothing for a very short time. These virtual particles are not normally observable. They exist for such a short time that they don't affect anything. They're just part of the quantum fuzz of the universe. But near the event horizon of a black hole, something different can happen. Imagine a pair of virtual particles appears right at the event horizon. One particle appears just inside the horizon, one just outside. The one inside the horizon can't escape. It falls into the black hole. But the one outside can escape. It can fly away into space. Normally, these particles would annihilate each other and disappear. But now they can't. They're separated by the event horizon. The particle that escapes becomes real. It's no longer virtual. It carries away energy. And here's the key. Where does that energy come from? It has to come from the black hole. The black hole loses mass. The event horizon shrinks slightly. This is Hawking radiation. Black holes radiate. They emit particles. They glow. They're not perfectly black, and over time, they evaporate. Let me say that again. Black holes evaporate. They lose mass, they shrink, and eventually, after an incomprehensibly long time, they disappear completely. When Hawking first calculated this in 1974, he couldn't believe it. He checked and rechecked his math. He thought he must have made a mistake, but the calculation was right. Black holes radiate. They have a temperature. The temperature is inversely proportional to the mass. Bigger black holes are colder. Smaller black holes are hotter. For a solar mass black hole, the temperature is about 60 billionths of a Kelvin. That's incredibly cold, much colder than the cosmic microwave background, which is about 3 Kelvin. So a solar mass black hole actually absorbs more radiation from the cosmic background than it emits. It grows, not shrinks. But a very small black hole, say the mass of a mountain, would be incredibly hot. It would glow. It would radiate furiously, and it would evaporate in a short time. The formula for Hawking temperature is T equals ρ divided by 8 by cmk divided by 8 by cm k by c by cis. Weierster reduced Planck constant. C is the speed of light. G is the gravitational constant. M is the mass of the black hole. And K Boltzmann's constant. Plug in numbers for a solar mass black hole. You get about 6 times 10 to the minus 8 Kelvin. Tiny. But plug in numbers for a black hole the mass of a large mountain, say 10 billion kilograms, and you get a temperature of trillions of Kelvin. Scorching hot. Such a black hole would evaporate completely in a fraction of a second in a burst of radiation. The time it takes for a black hole to evaporate completely is proportional to the cube of its mass. Specifically, the evaporation time is about 2. 1 times 10 to the 67 times m cubed divided by the solar mass cubed, measured in years. For a solar mass black hole, that's about 10 to the 67 years. That's 10 million billion years. The universe is currently about 14 billion years old. So a solar mass black hole will take 10 to the 54 times longer than the current age of the universe to evaporate. For all practical purposes, it's eternal. But not actually eternal. Eventually, it will evaporate. For a supermassive black hole like the one at the center of the Milky Way, with a mass of about 4 million solar masses, the evaporation time is about 10 to the 87 years, even longer. But for a tiny black hole, say the mass of a kilogram, the evaporation time would be about 10 to the minus 22 seconds, a tiny fraction of a second. It would explode in a burst of radiation almost instantly. When Hawking published this in 1974, it shocked the physics community. Black holes radiate. Black holes evaporate. This changes everything. Suddenly, Bekenstein was right. Black holes do have entropy. They do have temperature. The entropy of a black hole is proportional to the area of its event horizon. Specifically, S equals K dash your body, B times the area divided by 4 times the Planck length squared. The Planck length is about 10 to the minus 35 meters, so even a small increase in the event horizon area corresponds to a huge increase in entropy. When you drop something into a black hole, the event horizon area increases, the entropy increases, the second law is saved. This was a triumph. But it also created a problem, a huge problem, possibly the biggest unsolved problem in theoretical physics, the information paradox. Here's the issue. When the gas falls into the black hole, all the information about that gas, which atoms, which molecules, their positions, their velocities, all of it disappears behind the event horizon. Eventually, the black hole evaporates via Hawking radiation. But Hawking radiation is completely random. It's thermal radiation. It's like the glow from a hot piece of metal. It doesn't encode any information about what fell into the black hole. It's just random particles flying out. So where did the information go? The information about the gas that fell in. Is it destroyed? Is it lost forever? In quantum mechanics, information cannot be destroyed. Never. This is a fundamental principle. Quantum mechanics is unitary, meaning information is preserved. You can scramble information, you can spread it out, but you can't destroy it. If you burn a book, the information in the book isn't destroyed. It's scrambled into the smoke, the ashes, the photons flying away. In principle, if you collected all the ashes, all the smoke, all the photons, you could reconstruct the book. The information is still there, just spread out. But with black holes it seems like information is truly destroyed. It falls in, the black hole evaporates, and the information is gone. This contradicts quantum mechanics. This is the black hole information paradox. Does general relativity win and information is destroyed? Or does quantum mechanics win and information is somehow preserved? For decades physicists argued about this. Hawking himself initially believed information was destroyed. He thought black holes were the one place where quantum mechanics breaks down, but others disagreed. Leonard Susskind argued fiercely that information must be preserved. Gerard Hooft proposed ideas about information being encoded on the event horizon. String theorists developed complicated models trying to track where the information goes. In 2004, Hawking conceded. He publicly announced he had changed his mind. He now believed information is preserved. He proposed that quantum fluctuations at the event horizon might encode information in subtle correlations in the Hawking radiation, but even now in 2025, we don't have a complete answer. We don't fully understand how information escapes from black holes. This remains one of the deepest mysteries in physics. It's sitting at the boundary between quantum mechanics and general relativity, and we need a theory of quantum gravity to solve it completely. But here's what we do know. Hawking proved that black holes aren't eternal. They radiate. They evaporate. And this discovery opened up a whole new way of thinking about black holes, about quantum mechanics, about the nature of information and entropy. Hawking radiation has never been directly observed. The temperature of any astrophysical black hole is far too low to detect, but the theoretical framework is solid. The mathematics works, and most physicists believe it's real. Think about what this means. Every black hole in the universe is slowly, imperceptibly slowly evaporating, radiating away its mass, shrinking in the unimaginably distant future, long after the last stars have died, long after the universe has gone dark and cold. Black holes will be the last remaining structures, and even they will eventually evaporate away. The universe will end in a thin soup of photons and particles. Nothing left, no structure, maximum entropy. The heat death of the universe, but even more complete than we thought, because even black holes don't last forever. And this all came from asking a simple question. Can black holes have entropy? Wittgenstein asked it. Hawking tried to disprove it, and instead he discovered one of the most profound results in modern physics. Black holes radiate. Black holes evaporate. Nothing is forever, not even a black hole. That's the beauty of physics. You start with a question. You follow the mathematics. You trust the equations even when they tell you something bizarre, something that contradicts your intuition. And you discover that the universe is stranger, more subtle, more beautiful than you ever imagined. The speed at which this avalanche of understanding has progressed is staggering. Einstein developed general relativity in 1915. Schwarzschild found the black hole solution in 1916. Throughout the 20th century, physicists like Chandrasekhar, Oppenheimer, Wheeler, Penrose developed our understanding of stellar collapse, event horizons, singularities. Bekenstein proposed black hole entropy in 1972. Hawking discovered Hawking radiation in 1974. Each insight built on the last, each discovery opened new questions. And we're still avalanching along at high speed at this time. The Event Horizon Telescope is taking pictures of black holes. LIGO is detecting gravitational waves from black hole mergers. Theorists are working on quantum gravity, string theory, loop quantum gravity, trying to understand what happens at the singularity, trying to solve the information paradox. Every year brings new insights, new observations, new theories. That's science. That's the process. Start with a question. Do the mathematics. Test your predictions. And when the universe surprises you, when it shows you something you never expected, you don't dismiss it. You embrace it. You follow where it leads. Because the universe doesn't care about your intuition. It doesn't care about your common sense. It is what it is. And our job is to understand it. Nothing escapes a black hole? Well, actually, something does. Hawking radiation escapes, not from inside the horizon, but from right at the boundary. The black hole glows, the black hole evaporates, and eventually the black hole disappears. Hawking figured this out not by observing black holes, not by building experiments, but by trusting the mathematics, by combining general relativity and quantum mechanics, by following the equations wherever they led. And what they led to was shocking, revolutionary, beautiful. Black holes aren't eternal. They're temporary. They're dynamic. They interact with quantum fields. They're part of the quantum universe. And understanding them, really understanding them, requires a synthesis of everything we know about physics. That's the answer Stephen Hawking found, not comfort, not simplicity, truth.